Hello everyone. Today we'll be discussing about logistic regression and how we can interpret geometrically. So let's consider uh, the distribution of data to be like this. Like we have a set of points and some points here and another class of points and some points here. Sorry. Now, what logistic regression tries to do is it tries to find a hyperplane which tries to linearly separate the classes as much as possible. When I say classes here, this green point represents a positive class and the red point represents a negative class. And so what's the main objective of logistic regression is to find an plane which separates these values as much as possible. Like there could be some misclassifications as observed here, but still, uh, its task is to find a hyperplane which separates these values. And the equation of plane as studied in linear algebra ways for plane pi is W transpose x plus b equals to 0. And if this plane is if passing through origin, then this b value would be 0. Okay, and uh, imagine if we have a point here xi, and the distance of this point from this hyperplane, let it be di, then this di distance can be found by this equation, and this is a unit vector. So so the distance of a point, a positive point from hyperplane, is calculated like this. And imagine we have if we have to find the distance from the hyperplane to the negative point, let this distance be dj. So the distance dj can be calculated as the same formula, but the only difference is this point is opposite to the direction of hyperplane, so this would be negative. So for a point to be classified as a positive point, then W transpose Xi should be greater than 0, which implies Y will be positive. If W transpose Xi is less than 0, implies Y is a negative class. So this is very important that we should note. Yeah. So we defined our main objective of logistic regression is to linearly separate the classes as much as possible. So what this statement actually means, as discussed here, when case 1, when W transpose Xi is greater than 0, then Y is then uh, then Y is positive, which implies Yi into W transpose Xi is greater than 0. Then this is a correct classification. Let's consider when W transpose Xi is greater than 0 and Yi is negative, which implies Yi into W transpose Xi is less than 0. This is misclassification. Similarly, case 3, W transpose Xi, if it is less than 0 and Yi is negative. We saw here, right, when W transpose Xi is 0, or Yi is or the point is classified as a negative class. So when these two satisfy, then Yi into W transpose Xi is greater than 0, which is a correct classification. And the case 4, if W transpose Xi is less than 0 and Yi is positive or greater than 0, which implies my equation Yi into W transpose Xi is less than 0, which implies it is misclassified. As you can see, for the points to be correctly classified, this condition has to be satisfied here as well. So, what we are essentially trying to do in a logistic regression is we have to, if I formulate it mathematically, we have to, uh, as seen here, we have to maximize this value for all the data points, which implies summation of yi into w transpose xi. This value for all I equals to 1 to n. This value has to be maximized, and this can be written as an argmax. So and you know here yi and xi are constants, those values won't change. Only variable is our weight vector. So we have to maximize this equation for some w. So essentially we are trying to find optimal weights for our plane, which will maximize this equation. However, there's one problem with this equation. Uh, First, I'll tell you an example, and I'll explain you in detail and how we can handle that. So imagine we have some data points here. Let this be positive points, and we have equal number of negative points on this side. Imagine these are negative, and we have a plane which separates this. Okay, and let's assume the distance from the plane to these points is 1 unit. Similarly, here it's also 1 unit, the distance. Let's consider we have a point which is very far from the plane, uh, here, and the distance from this point to the plane, say this is of 100 units, assume. So and let this be a negative point, and this be the direction, and let this be the direction of the plane. Now if I have to calculate my w star here, so what's it doing? It's essentially summing up the sine distances. Okay, this is also called as sine distance. So if we just uh, calculate this value here, how many positive points we have? 1, 2, 3, 4, 5, 6. 6 positive points. So my yi is 1 into, and instead of saying that, my sign distance is 1 for this, 1 for this point, again 1. So like that, 1, 2, 3, 4, 5, 6. 6 positive points. 4, 5, 6. And we have 1, 2, 3, 4, 5, 6. 6 negative points here. So, however, these are in the opposite direction of the plane. So this is negative into -1. So that would be uh, instead of saying that, this would be like, this will be with negative, and this will also be a negative coefficient. So in total, in return, it will be a positive one. 1, 2, 3, 4, 5, 6. However, we have a negative point here, which is in the direction of the plane, but distance is 100. So this value becomes here -100. So if I calculate, it's for the resultant value would be 6 plus 6 is 12. 12 minus 100 is minus 88. Now let's consider the same 6 points. 1, 2, 3, 4, 5, 6. 6 positive points, and 1, 2, 3, 4, 5, 6. 6 negative points, and the same outlier which is present here. However, this time let's consider, instead of this plane, let me mark it as pi1 here. Let this plane be pi1. What if our plane is like this? Okay, and this is the direction of the plane. So, and let this be a unit distance. The outlier point is 1 unit away from the plane, and the distance from the plane to the positive point is 1 unit, and subsequent distance is 1 unit. So this part will become 2, this part will become 3, like that. This 1 unit, this 1 unit, this 1 unit, this 1 unit. So this if we calculate our sum of sign distances, this would be 1 plus 2 plus 2 plus 3 plus 4, 5, 6. And this value, oh, the direction will be like this. I'm sorry, not this. Yeah, so this value will be -1, -2, -3, -4, -5, -6. And this value will be +1. What happens is all these values will be negated, and only this value would remain. And it says the sum of sign distances is 1, and this value is better than the value here. So what it's essentially saying is the best uh, plane which can linearly separate the values is this one. However, if you observe, this is an incorrect way of classifying the points, because here there are 12 misclassifications if we consider this as a correct plane misclassification and one correct classification. So this this is this is not the correct plane which can does it. But how here we have 12 correct classifications and one misclassification. So we know this is the correct hyperplane. But if we consider only the sign distances, then it suggests this is the correct hyperplane to do the classification. So to summarize, outliers will impact if we consider only the sum of sign distances, only this part. So how do we handle this? So to handle this, there's something called as squashing. Let me, yeah. So to handle this, there's something called as squashing. What it says is we have to handle very large values of x, and we have to uh, um, and if xi is not large, then keep as is, which states like we have to identify a function which takes care of these large values of x. And uh, we know a sigmoid equation. The equation of a sigmoid function is 1 by 1 plus e power minus x. And let's look how that function looks like. Plot 1 by 1 plus e, e power minus x. As you can see, when x becomes large, imagine when x becomes large, my y value just tapers off. And when x is considerably small, it's not small as a decent value, it increases in a linear fashion. So we can modify our uh, objective function, that is w transpose argmax. We have to find argmax of a w where it maximizes our sign distances into w transpose xi. To handle the large values of x, we will uh, update this function like argmax of w I equals to 1 to n sigmoid of yi w transpose xi, which is equals to argmax of, which is equals to, like, here the x term is this part, so we have to substitute here. So this will become argmax. We have to find a w, a weight vector, which maximizes this function 1 by 1 plus exponential of yi, oh, minus yi w transpose xi.